Okay, let's review what we talked about last time. So the last thing we talked about is the Born's rule. So let me start from the normalized state. So in quantum computing, we assume that every quantum state is normalized in the following sense. So a 1-qubit state let's say alpha 0, alpha 1 is normalized if so these coefficients are complex number. So whenever you want to compute the probability or any kind of strength of a quantum state, you have to take the absolute value. Don't forget, it's not the square, it's the absolute value. So if it's 1, then it would say it's normalized. So we don't really distinguish what a state is normalized or non-normalized state, because every state will be normalized. We assume that every quantum state is normalized when we talk about a quantum state in quantum computing. But I have to be clear. And the normalized state of an n-qubit state is defined inductively like this. A n-qubit state let's say psi n so since it's n-qubit state, it's a tensor product or linear combination of tensor product. You can split each of the sum end in your linear combination as a tensor product between the 1-qubit state and n minus 1 qubit state. So this sum end has 0 ket on the 1-qubit state, and we can have another one because we're always talking about the base of 0 ket and 1 ket. And let's call psi 1 n minus 1 to be another n minus 1 qubit state. When we talk this way, the 1-qubit state on the left-hand side of each of the sum end of the tensor product represent the quantum state of a same qubit. So for example, here we're talking about the quantum state on the last qubit on the n-qubit system. So we have n number of quantum material that each contains 1 qubit state, and we're talking about we fix one cubical material, and then we talk about that quantum state for 0 and 1 here is normalized if alpha 0 square, alpha 1 square is 1, and these are also normalized. And what do you mean by n minus 1 qubit state is normalized? If we talk about n qubit state is normalized, we are defining normalized state inductively here. So for example, if I have n 2 qubit state, when n is 2 here, then this n minus 1 qubit state is 1 qubit state. So if I want to say a 2 qubit state is normalized, I have to be able to split my quantum state into sum of 2 tensor products. And if I take the first qubit, I mean the qubit 1 here, and then qubit 0 state for each tensor product has to be normalized state, which go back to the first definition of normalized state for 1 qubit state. So easy way to think about whether the quantum state is normalized or not is just simply take all the coefficients for each base state and then square sum. like taking the square absolute value and then square sum and check whether it becomes 1 or not. So here's an example. Here, I'll give you an example here. So let's look at this one. 3-qubit state. So we're not including all the base state. We're only having 6. So which means that rest of the 2 base state have coefficient 0. And let's check whether it's normalized based on our definition here. So first, let's try to fix the qubit 2 here. So here, the qubit 2 has 0 ket for the first 3 summand here. So each of these are tensor product. I mentioned that this is abbreviated notation for tensor product. And the second 3 has 1 ket. And okay, so here, let's see. Yeah, well, maybe let's just naively think first. So 2, 3, 0, 0, 1, 6, 0, 1, minus I 6, 1, 1. Okay, so that's the first 3 combined as a 1 tensor product, and the second one. So I put all the coefficient inside the parentheses for now. I will take out after normalize these further, so don't worry about that. So we have 1 over 2 square root of 3, 0, 0, and I square root of 5, 12, 0, 1, and I square root of 2, 1, 1. Okay, so I want to normalize these two qubit state. So let's think about how we can normalize this. So, I mean, this is not normalized state at all. Let's look at the, so let's say this is 0, I 0, 2. So since it's not normalized, let's put the prime here and 1, 2 prime. And let's look at this, the first state. I can further split that into the sum of tensor products. Let's say 0 tensor product, 2 square root of 3, 0 plus square root of 6, 1, and then minus 1 tensor product, I 6, is it square root of 6? Yes. Here, square root of 6, and just 1. All right, so now we're looking at the 2 qubit state, and let's go back to our definition of normalized state. And of course, this is not normalized state, but let's try to make it normalized state by multiplying some constant. So in other way, if I put it this other way, what kind of coefficient should I put on top of this psi 0 prime 2 in order to make this as a normalized 2 qubit state? So first, look at this. So this is not normalized because if I square sum these coefficients, because that becomes, what is it? 1 over 2, 1 over square 12, and 1 over 6, and it becomes 3 over 12, so it's 1 over 4. So it's a square sum. So what I have to do is I have to take that out, take that out, 1 over 2. And then if I take out 1 over 2, I get 1 over square root of 3, 0, and when I take out these, so 2 over square root of 6. Yes, so we have 2 square root of 6, right? Yeah, maybe I can make it further simpler. 2 over square root of 3 here. Yeah. So this is normalized. Obviously, if you take the square sum, then it becomes 1. So now I know that I need 1 over 2 as a coefficient of 0 in order to make it normalized state. So let's just ignore the tensor product from now on. And then the cat 1 is also already normalized, so I don't need this, right? So you can choose whether to leave this I in here or take out I with square root of 6. It doesn't matter because we're talking about normalized state. So let's take out all the coefficients here. So I is already size 1 complex numbers. So now, okay. So we have this quantum state. I also want this to be normalized. So let's check the square sum of these two coefficients, 1 over 2 and I over square root of 6. So it's 1 over 4 plus 1 over 6. So this is 12, 3 plus 2. So I know that, okay, so this is 5 over square root of 12. So I need to take out 5 over square root of 12. And then, what is it? It's going to be 5, 12, 1 over 2, and then 0, and square root of 3, 0, plus 2 over 3, 1. And also I need minus 5 over 12, I, square root of 6, I, 1, 1, yes. So so inside of parentheses is normalized state, but the whole thing is not normalized because I have this number multiplied on that normalized state. So I can define my psi 0 to be the normalized state of that quantum state, psi 0 prime. So it's going to be this. And okay, let's go back to here, even though I didn't finish the psi 1 and prime 2 here yet. So prime, psi cat is going to be, first it was 0 tensor psi 0 prime 2. And also we have this. But then I can replace this by these two. So we have square root of 5 over 12 and 0 tensor product and psi 0 2. So psi 0 2 is here. And then we can do the same thing here. So without actually computing, I can find it, but let me leave it like blank here. So 1 and here. So this is the normalized state of this state. Okay. Well, let's try. Let's see how we can find this one. So here's easy way you can find the strengths. The strengths or you can call it norm because it's a vector. The quantum, we are talking about n-qubit state, and n-qubit state is a vector, so we can replace the word strength as a norm square of, let's see, psi n, and let's call it this way. So I'm gonna make a notation like a alpha 0, 0, 0, 0, and alpha 1, 0, 0, 0, 1, and up to alpha 2 to the n power minus 1, 1, 1, 1, 1. So in other words, it's just alpha n, where n is not a good index, so m n, where m is from 0 to 2 to the n minus 1. So we introduced another notation of writing down the tensor product of the base state, because if you just have a list of zeros and 1, it is nothing but representation of a integer in a binary representation. So I can just replace this as 0, 1, and 2 to the n minus 1. So if I have n-qubit state like this, then the strength of this quantum state is sum of alpha m from 0 to 2 to the n minus 1. So using that, let's compute the strengths of this 2-qubit state, psi 1 prime 2. So it's 1 over 12 plus 5 over 12 and 1 over, is it 2 over 2? I think. 2 over 2, yes. I think I made typo here. So 3, I think. So 2. That's 7 over 2. The strength is 7 over 2, but we have to take the square in order to get the norm here. So we get 7 over 12 here. Okay. So what do you see? So I just changed the representation of my quantum state of 3-qubit state and given as this long form into a short form. And if I want to check whether it's normalized or not, I don't care what this is because it's already normalized. I need to check 2 coefficients of the one fixed qubit are summed to 0, square sum to 1. So I know that since 5 over 12 plus 7 over 12 is 1, therefore this psi 3 is normalized. And also, if you use this remark, you can see that this 3-qubit state is normalized directly from this coefficient. So you just take the square sum of absolute values, and then you can see that it's equal to 1. Okay, is it clear? All right, so Born's rule. What is Born's rule? So the probability of observing x, where x is 0 or 1, on the 1-qubit state, alpha 0, 0, alpha 1, 1, is the probability observing, it's just x, okay, so is alpha x alpha 1 square. So that's the Born rule. So whenever you have a quantum state, supposedly have a quantum state as a linear combination of ket 0 and ket 1, then this is our chance. Okay, and since we always assume that if the quantum state is normalized, if psi is normalized, then we can just simply say that the chance is just the squares of the absolute value of the coefficient. And that's the Born's rule for the 1-qubit state. And there is a Born's rule on the n-qubit state, and it says the following. It really says it doesn't matter the quantum state on the other qubits. So if psi n has alpha 0, 0, psi 0, n minus 1, and alpha 1, 1, psi 1, n minus 1. And let's say this is quantum state of qubit I. So you'll see what I mean by that, because usually we put the index from the right to left as increasing order, but sometimes you want to choose a random qubit here in the middle of this order. And if you want to express as a tensor product in this way, you have to switch the order of the quantum qubit. So we assume that this is somehow reordered qubit state, and I assume that this is quantum state of qubit I, and the probability, and then also this is normalized, and the probability of observing X on qubit I is the same. We only need to look at this coefficient. So this is only when we have normalized state. So these means these n-1 quantum state are already normalized. And that's not everything about the Born's rule. It's not about just the probability. What was other part in the Born's rule? So it's basically about the measurement. So you take the measurement, you get result, either 0 or 1 if your base is 0, 1, and 0 ket and 1 ket. And what happens to next? What happens to the rest of minus 1 qubits? N minus 1 qubits. So it collapses. So remember what I said in as a theorem, as a Born's rule. It collapses to the state, right? So for example, if I take a measurement on the 1-qubit state, suppose that I observe 0, then everything collapses to 0. The quantum state collapses to 0. Before the measuring, it has 0 ket and 1 ket simultaneously. So it's a superposed position, a superposed state. But after measurement, except for the measured state, other states are disappear. It's gone. So same thing happens in the n-qubit state. If you take a measurement on 1 qubit, let's say qubit I, then let's say we observed 0 here. Then this state, so quantum qubit I state is collapsed to 0. That means there's no ket 1 state left in the qubit I. So therefore, there is no quantum state psi 1 left in the rest of the n-1 qubit. So automatically, once you take the measurement, you kind of change the state of n-1 qubits. So that's where this weird thing happens, and that's where actually the power of quantum computer comes. So here, let me define the important terminology that in the quantum computer and also quantum mechanics. So definition, a n-qubit state is called an entangled state if it is not a tensor product of n one-qubit state. So you have to understand what is n-qubit state clearly in order to understand the meaning of entanglement. So n-qubit state is not the tensor product of one-qubit states. It's a linear combination of tensor products of one-qubit states. Okay, not just one tensor product. It's a linear combination. So when you say n-qubit state, you can have many tensor product state superposed together. Superposed means literally just the linear combination. And then that's the general n-qubit state. But there's a special kind of n-qubit state. It's called entangled state, which can be represented as the tensor product, single tensor product of n one-qubit states. So for example, here, so if I write 1/2, 0, 0, 0, 1, square root here, then I can split them into tensor product. 0 tensor. Let's say I just mentioned this way. So 0 ket and 1 ket. And actually, this is normalized there. So better way to put this is the tensor product of 2 normalized one-qubit states. So I should put the 1/square root inside this tensor product. So this is better way to put it. And as we defined it, it's a tensor product of 0 ket and plus ket. Okay? So is this entangled state? It's not entangled state. It can be represented as a tensor product of 2 one-qubit states. So it's not entangled state. Entangled state is something that we cannot write as a tensor product. So this is not entangled. So what do you mean by it's not entangled? It means that if I take any measurement, then there is a fixed state. There's the quantum state of the other qubit is not dependent on the measurement of one qubit. So for example, if I take a measurement here, there's only one chance that I get. There's only one thing I can get. I will always observe 0. And whether or not I take a measurement, the quantum state on this qubit will be always plus ket state, right? So it doesn't really matter whether or not I take a measurement. But let's look at this other quantum state. Yes? No. Oh, so that's a good question. So let me write terminology again. So definition. So the question is whether the plus ket is entangled state of 0 ket and 1 ket. And you have to distinguish entanglement and superposition. Okay, so there are two different terminology. The plus ket is superposed state. It's not entangled state. So a quantum state or a quantum state is said to be in a superposed state. If it is a linear combination of two or more quantum states. So, for example, the general shape of the superposed state is like this. And you can have more. It's one. So one, and yes, n, and you can have more. If you have a k n qubit state, then you can add them together to say our quantum state is superposed. So this plus ket, which is 0 ket plus 1 ket, is a superposed state of 0 ket and 1 ket. So entangled state is not superposed state in some sense. If you are superposed state, I mean, it's not really different. It's not related. Sorry, so it's not related. It's not kind of same idea or the opposite idea. So you can have a superposed state for any n qubit state, but entangled state only applies for 2 qubit state, 3 qubit state, or n qubit state when n is bigger than 1. So you cannot say anything about the entanglement when you have a 1 qubit. It's only for multiple qubit. Okay. Any other questions about the definition? Yes. Okay, yes, let's give an example of entangled state, the famous example and simplest example. So let's say we have psi as 1 over square root of 2, 0, 0, plus 1, 1. This is entangled state. So it's an entangled 2 qubit state. Why is it entangled? By definition, you cannot write it as a tensor product of two 1 qubit states. So if you try to do that, like if you try to find out what is, let's say, psi 0 and psi 1, where each of these are 1 qubit state, and what would be the coefficient of these two 1 qubit states that satisfies that the tensor product equals to this, you cannot find the coefficient. There's no such psi 0 and psi 1 ket satisfies this equation. So nothing can have the equality here. So this is entangled state. And also it's normalized, right? You can see that it's square root of 2, 0, 0, square root of 2, 1, 1. So if you try to take a measurement on the qubit 0, then the other qubit is already normalized because you ket 0 and ket 1. So, and also the coefficient here are square sum to 0, 1. So the chances observing 0 and 1 on the qubit 0 is 50 and 50. And also chances to observe 0 and 1 for the qubit 1 is also 50-50. Okay? So it's a normalized state, and we can take a measurement. And the weird thing happens from here. So here, let me draw out. I'm not good at drawing, but I try to make it into a cartoon here. So let's say I have qubit 0 here, and here I have qubit 1 here. And then these two qubits are entangled. So it has 1 over square root of 2, 0, 0, and 1, 1 state combined together. Okay? So these are combined, entangled. They're literally entangled here. And so here we take a measurement. So basically measurement is look at the qubit. You take a tools and observe the qubit. So Alice. So Alice, Bob, and Eve are the common names that appears in the computer science, right? When you take a, so this is Alice. She watches the qubit 0. And here's Bob. Okay, Alice watches the qubit 0 first. So, and then Alice saw, let's say, it's 0, okay? So this happens first. This happens first. And then Bob sees the qubit. What can he say? I mean, there's no choice. Bob has to say it must be 0. And he will see the 0, but even before he takes the measurement, he knows that it must be 0 if he knows that Alice observed 0, right? So do you think it's something weird going on? So in the mathematical settings, nothing is weird because, okay, so we have a Born's rule. If you observe a quantum state and it collapses to that state, and because it collapses to that state, the other state disappears. So the other qubit must be fixed into one of the tensor products in the entangled state, in superposed state, sorry. And this bothers a lot to physicists, including Einstein, when it's first introduced. Probably have heard about this. This is called the spooky action at distance. So Alice take the measurement. She did something to the qubit. And instantly, I mean instantly, not in the speed of light or anything. It just changes the qubit 1 state instantly. So can we think this as a transfer of information in an instant time? It doesn't make sense because if you want to transfer anything, any information, it's a kind of a, in the materialistic view, nothing can transfer, nothing can travel faster than the speed of light. But it's not just faster than speed of light, it's instant. How can it happen? That's the question. That's the basic question in the what's called so-called spooky action at distance. So, okay, so the assumption is, okay, you probably cannot separate the qubit 0 and qubit 1 as a material, two materials. Actually, you can. There are two quantum material separated by distance, whether it's short or not. It's actually two distinct material, and then you can make it entangled together. So you can, yes, separate these two materials. So these are physically separated two objects. You take one measurement, it instantly changes the other object. So it does something to other object. So if you think it that way, this is not coincide with our intuition or physical laws. So there's a science fiction called Three-Body Problem. Have anyone seen the Three-Body Problem? It's a Netflix drama. And in Three-Body Problem, there is an alien species that try to invade Earth, but they cannot they cannot travel faster than the speed of light, so it takes a long time. And the novel says it takes 200 years to get to the Earth. But they sent quantum, or what is it called, photon or something like that. It's kind of a small particle that moves as fast as the speed of light first before they come to Earth. And then the photon, actually there are two photons traveling around the Earth, and then they're communicating with the people on the Earth and the alien on the spaceship before they arrive there. So it took many years to send the photon first, because photon can travel at almost as equal speed of light. It arrived in like 50 years. And for the spacecraft to get to the Earth, it takes longer time because it's actually not as fast as the speed of light. So the photon on the Earth and the photon on the spacecraft are communicating because of with the entanglement, because they entangle these photons before they send to Earth, and then when they send the photon to the Earth, since they are entangled, whatever the photon do on this Earth instantly changes the state on the photon on the spacecraft, and that's just a novel. That's just novel, so that they can communicate with the people on the Earth and the people on the spacecraft, alien species, instantly. But that's not the way this entanglement works. That's not true. It's not really the transfer of information. So it's really, um, I wish there is a nice explanation that everyone can understand. What is the entanglement then? But I don't think there is. Other than this entangled state is just a vector space. Just a vector. The state represented as vector and follows the Born's rule. So if you try to think about this entanglement as a with your imagination, you can write a novel, but nothing practical will happen. So, for example, even if you want to say it's the transfer of information, how do you know that the Alice got 0 instantly before you take the measurement? So Alice and Bob could claim that they took a measurement at the same time, right? But how do you know that they measured at the same time? Right? The time is also relativistic. I'm not a physicist, so I may be wrong. So you don't know whether they took the measurement at the same time. And also, if he wants to confirm that he got 0 before he take a measurement, I mean, if he wants to claim that information is transferred faster than the light, then he needs to know, and he needs to take a measurement. So let's say, here there are certain distance placed apart from 2 qubits, like say distance d, and then the speed of light is c. So it takes d over c amount of time to transfer the information, right? So let's say Alice took a measurement at time 0, and then Bob took a measurement at the time epsilon, where epsilon is less than d over c. Okay? So if he claims that the transfer of information is done faster than the speed of light, he needs to measure take a measurement after Alice take a measurement at time 0. Within the time d over c, Bob has to take the measurement. And also, he needs to know that Alice already got the results 0 before he take a measurement. I'm not sure whether that makes sense or not, but anyway, there's no way he can confirm that transfer of information is done faster than the speed of light unless he get the information faster than the speed of light, right? So it's kind of a spiral spiral logic here, so circular logic. So intuitively, we want to understand every information is transferred materialistically, but in this case, it's not really transfer of information. So the assumption is wrong. We are not transferring information. So what is that? What is the measurement do to us? What is the measurement on the entangled state? Well, it's just the collapsing of state. It's not transferring the information. That's all. We're just collapsing the state. Does anyone want to make a comment on this? Because I may be wrong.
Bob know that Alex observe as zero after t is over d over c.
Mm-hmm. Yes, at least he needs some time, which cannot travel. I mean, the information has to travel through, let's say, wire or electric communication or anything materialistically. Then he needs more time than d over c. So he will find out that Alice observed zero after he took a measurement, right? I mean, even if he claims that he took the measurement at the same time, what he can find out that the entangled state works because Alice took the measurement zero and Bob took the measurement later, way later. Bob found out that Alice got zero and he got also zero. Oh, okay, so then our measurement on the entangled state actually follows the principle here, Bohn's rule. And that's all. He just claimed that Bohn's rule is true by evidence. And it's not the transfer of information. It's just an experiment. It's just an experiment that shows that Bohr's rule is true. So actually, this is not the only thing that bothers Einstein. There's one more thing. It's called the hidden variable. So I'm actually hidden variable is not really about the entangled state. It's actually about the superposed state. So the quantum computer, or quantum state, the principle of quantum state is that you can have 0 state and 1 state at the same time. So we understand that it's okay. That's what the quantum mechanic claims. But if you think a bit deeply, it gives very unintuitive situations. So so I will introduce some kind of operation here. So we're gonna talk about the quantum gate shortly, but for now, let me just introduce one quantum gate here, which is called Hadamard gate. So Hadamard gate is an operation acting on the set of 1 qubit state. So how does it act? So the set of 1 qubit state is a vector space. So if you want to understand the action, you only need to see where the basis state goes. So Hadamard state sends 0 state to 0 state. Plus state. And Hadamard state sends 1 state to minus 1 state. That's a Hadamard. So let's say I have the 3 qubit state, psi, and originally it was 1, 0, 0, 0, 1, 0, and 0, 0, 1, and 1, 1, 1. can you see that it's normalized state? Yes, there are 4 states and each has 1/2. So if you take the square sum, it's 1. So now I have 3 scenarios. I'm going to apply Hadamard gate on 2 of these 3 qubits. So here, first, take the Hadamard on qubit 0 and 1. That's the first. And second, H. So there are 2 Hadamard gates acting on 2 qubits. So Hadamards on qubit 1 and 2. And third scenario is Hadamard on qubit 2 and 0. Let's see what we get. So if I apply the Hadamard 0 and 1, let's say 0, 1 here. Now you change the state, of course. Let's see how it changes. It's 1/2. So we're taking index from the right to left. So 1 plus, okay, for the first one, 1, 0, 0, because 1 plus plus, and then 0 minus plus 0 plus minus 1 minus minus, right? And then let's expand it in terms of 0 and 1, because plus and minus are just the superposed state of 0 and 1. Let's see, how can I do it in a clever way? So let me do the computation on here and write the answer on this board. So let's do the computation here. So the first one, 1 plus plus. So let's drop all the strict notation here. Just 1 plus 1, 1 plus plus becomes 1, 0, 0, 1, 1, 0, 1, 0, 1, and 1, 1, 1, right? So, and all the signs are plus. Does it make sense? Maybe I have to expand this one, and then I can abbreviate the other one. So what does it look like? So it's 1 over square root of 2, 0 plus 1, and 1 over square root of 2, 0 plus 1. Okay, so I can take out 1 over square root of 2. Actually, it's not really important. It's 1 over 2 anyway. And then let's distribute each tensor product here. So 1 is fixed, so it's 1. And if I take this one and this one, it's 1, 0, 0, right? If I take this one and this one, it's 1, 0, 1, right? And then here, if I take 1 and 0, becomes 1, 1, 0. If I take 1, 1, and then it's 1, 1, 1, right? So I can write 1 plus 1 plus is 1, 0, 0, 1 plus 1, 1, 0 plus 1, 1, 1. So let's drop the cat notation here to make it faster. Then how about 0, 0 minus plus? So here, remember that minus has a minus sign on the 1 cat. So I have to be careful. So first one, 0, 1, 0, 0, 0, it has plus sign. But 0, 1, 0, so 1 is taken from the minus cat here. It has a negative sign. So we need minus here, minus. And then 0, 0, 0, 0, 0, 0, already taken. So 0, 0, 1 has plus sign. Then and another one is minus, very sorry, so not 1, so it's 0 here. 0, 1, 1 has a minus sign here. Okay. So next one, 0 plus minus. That makes sense? Everyone makes sense? I'm taking this one, dropping all the cat notation. So 0 plus minus 0, 0, 0 plus 0, 0, 0, 1, 0 and minus 0, 0, 1, 0, 1, 1, right? And then how about this one? So I have minus sign here, so let's put minus here. Minus, minus. So it's a minus of 1 minus minus. So 0, 1, 0, 0, minus 1, 1, 0, minus 1, 0, 1, and plus 1, 1, 1. The reason why I have plus 1, 1, 1 is that it has 2 minus on the 1 cat for both of these minus, so we have plus here. So let's add all this together. So after taking Hadamard, everything is changed into these states, and it's a superposed state of these. They are canceling out. So first one, this is canceled out, and this one is canceled out. My minus sign here, and this one canceled out, and this one is canceled out. So what do we have? These things. So we can combine them together. So basically, we have 4 of them, and you can check the coefficient later. So its coefficient is 1 over 2 again. So first one is, let's say, 0, 0, 0. And what? 1, 0, 1, yes. And 1, 1, 0. There are 2 of them, 1, 1, 0, right? Yes. And also minus of 0, 1, 1. Yeah, there are 4 of them like this. How about when I apply the Hadamard on 1, 2? So can you guys do the computation here? So try to put the Hadamard on 1 and 2, which is the 2 on the left side here. Just take the computation I did similar to what I did in the first step, and then give me the answer. I'll give it some time to compute. So don't forget, we're still talking about the hidden variables, but also it's a exercise for taking a superposed state and computing quantum state. Yes. Which part was it? 1 over 2? Yeah, but yes. So I dropped. So this one already have 1 over 2 here. Everything have 1 over 2. And also, we already have 1 over 2 on here. So have guys got the answer for the second part? All right. So what is the? So there are 4 states. Can you name all these 4 states? Anyone? Need more time? Okay, you got something here. Okay. So what's the state? So 000 is here. And what else? What do you have? Plus 0. Wait, 0 what? 0 1 1. And minus 1 1 0. Yes. Yeah. Yes. Everyone got the same thing here? Okay. Okay, so let's do third one in our head with our heads without thinking, without writing down. So I'm putting Hadamard on the left one and the right one. So whenever you put the Hadamard when it's 1, it makes a negative, and negative has a negative value on the cat 1 state. So keep that in mind. What we have here is that you want to combine these two, right? It has the same 0 cat on the middle one, which has no Hadamard applied. So in that case, you have 0 1 0 0 0 minus 1 0 1. And then you want to combine these two, which has 1 cat on the middle one, which has no Hadamard applied. So we have 0 0 and 1 1, but you have a minus sign here. So what is left is plus 1 1 0 and 0 1 1. Okay. Okay, so here now it becomes interesting, very interesting. So let's say x0, x1, x2 be the measurement outcome of, so we're going to measure each 3 qubits, each of 3 qubits, okay? So every qubit is measured, and this is the measurement outcome of qubit 0, 1, 2 without Hadamard applied. Okay? So that's the symbol, just x0, x1, x2 is either 1 or 0. Okay? Just a symbol to represent 0 or 1. And let me write another notation. So these one, which has a h on the superscript, is measurement outcome of these qubit when the Hadamard is applied, with Hadamard applied. Okay? So let's look at the first one, the original state. Let's see the original state. So you can observe either this or this or this or this. There are only 4 possibilities to observe the quantum state and the measurement outcome. So we're going to just take these 3 variables, x0, x1, x2. No Hadamard is applied in the beginning. So let's suppose that we apply the measurement here, and no matter what that is, if I add this 0 and 1 with a binary addition, so this here, it's not the integer addition, it's a binary addition. So 0 plus 0 is 0, 1 plus 1 is 0, something like that. So binary plus. So what is it? If you observe 1, 0, 0, if you add all three binary number, it's 1. Here, it's also 1. Here we have 1. Even when you have 1, 1, 1, you add binary numbers with binary addition, it's 1. So your answer will be 1. Now, suppose that we have the same quantum state and then measured after taking Hadamard on 0 qubit and 1 qubit. So this is H, X0H. Because we applied Hadamard, this quantum state on the qubit 0 and qubit 1 is changed. So we're going to use the different symbols, different variables to represent the measurement outcome. And we didn't apply the Hadamard. So qubit 2 is intact. Nothing happened. Nothing happened here. So now their possibility are 4. When you have 0, 0, 0, what's the binary sum of these three variables? 0. And if you got 1, 0, 1, binary sum is also 0. And same for others. Now let's look at the second and third. We have x0 plus x1h, x2h. What's the binary sum? Look at the state. 0, right? And the last one, not this one, it's also 0. Can you see weird thing here? Let's add side by side. So you see there are 2x0, 2x1, 2x2, and 2x0h, 2x1h, and 2x2h. So there are 2 of each. So no matter what these values are, if you have 2 of them, whether it's 0 or not, then they sum to 0. So on the left-hand side, it must be 0. But on the other side, if you add 0 and 1, well, there's only 1 1 here, you get 1. So you conclude that 0 equals to 1.
What is this plus? What is the definition of plus?
So plus is just binary sum. 0 plus 0 is 0. 1 plus 1 is 0. 1 plus 0 is 1. So if you're not, so it's nothing wrong with the binary addition. You can do it with the parity, even or odd. So you get the even number here, you get the odd number here when you just sum the integers. So it means the even number equals to odd. It doesn't make sense. So where did it went wrong? Which part was wrong? Where do you think it's wrong? Where do you think it went wrong direction? Okay, so assumption is not wrong. The Hadamard gate is there. It actually exists, and it changed 0 to plus. And also, you can make this state too. This is perfectly legitimate state. You can make this state. Literally, you can make this state with a quantum computer. And there's no error in our application. Yes?
How to get measurement from the quantum state?
How to get the measurement? You take the measurement on qubit 0, qubit 1, and qubit 2. Well, let's say if you take the measurement on qubit 0, there are 50-50 chance to get either these two or these two. So you can rewrite this as 0, 0 plus 1, 1. So let's drop the coefficient here for now. So you might think that measurement stage is something wrong here, but let's see. Let's check whether it's wrong or not. So I'm gonna drop the coefficient. I mean, if you want to, you can take 1/2. Okay. So anyway, if I take a measurement, you can either see 0 or 1. Suppose that you got 0, then the rest of the 2-qubit state are collapsed to this, and then you take the measurement of qubit 1 or qubit 2, then you get either this or this, right? So eventually you end up having one of these 4 base states. So it doesn't matter which one you get, because what we are doing is looking at the parity of numbers, parity of sum of numbers. They're all the same, right? So parity of the number, sum of numbers are the same. So actually, since we have not much time here, this is wrong. You cannot assume that there is a variable that stores the information, that you're going to store the information of the measurement outcome. Why? So in fact, you can, but if you assume that there is a hidden variable, this is called a hidden variable, that you will get some output which you can expect after the measurement, then what you can do is this kind of computation. So we assume that this one, let's say x0 and x0 are the same x0, right? Because we didn't do anything on the qubit 0. We didn't apply the Hadamard on the first step or this step. So qubit 0 is intact. Nothing happened here. In fact, nothing happened. So therefore, you can imagine that if I take the measurement on qubit 0, it must have same output. So you can imagine you have 3-qubit state, 3-qubit state here, here, and here is your time. And I took a measurement here. Okay, so this is time. And I got the result. And then, so there are many possibilities. So this is some kind of, quantum state material. And you took the measurement here, and time passed. And when the time passed, you can have no chance to retrieve the same quantum state. So even if you make another quantum state has the same information, you can claim that this is not the same thing from before. So only you can get the same thing, the exactly same thing, is get the time machine. There's no time machine, but suppose that we imagine there's a time machine and you went back to the past before you take the measurement, and you take the measurement at the exact time of the exactly same material again, this time after you take the Hadamard on x1 and x2, but you didn't do anything on the qubit 0. So qubit 0 is supposed to be the same thing, but you will not get the same thing again, because if you do, then you have to assume that this x0 and x0 are the same thing, and all the other part is the same thing. So you will get the contradiction here. So why is it not intuitive? Because we sometimes think that, okay, so this is atom, so this is like a proton here, and here's an electron here, and we kind of think that the quantum material is measuring where the electron is, depending on the distance, depending on the direction. We say electron is up or down. So it's kind of imagine that electron is spinning around the proton, and then at one spot and one time frame, we observe where the electron is, right? So if you go back to the same exact time with a time machine, we'll get the same exact position of the electron in an atom. But that's not true in quantum computing and also quantum mechanics. In fact, electron is not a moving object, it's a state. It's a, it's a probabilistic state, right? That's quite, I mean, we kind of know that. We know that, but we still think that if you go back to the time machine, if you go back to the past, things will happen exactly the same way because that's the way of the law. If you have a push and something will move, right? There's a causality. Something happened because of that, and because of that, something other happens. But in quantum mechanics, no, there's always different outcome. Even you have the same, exactly same material. So I think this somehow bothered Einstein because Einstein said God is not rolling a dice, right? He didn't want to believe that this is all just random, right? If you have a certain the reason, some kind of a motivation, then it could be a force or other, thing. Then he wants to get the same outcome. It has to be the same outcome. But the quantum mechanics says no, it's just by chance. So you cannot assume that these two are the same thing, right? So think about this, and then you will find it every every time you think about it deeper, you will find it is more interesting and also not make sense. But in the same time, perfectly makes sense if you think of this in a mathematical setting. Just take it as vectors, only take the principles and take the computation, everything works. If you start thinking about this as a physical state, physically existing state, and you try to apply classical understanding of physics, then it doesn't make sense. So that's why I think the quantum computing is literally the mixture of mathematical subjects and the physics subject. You cannot understand this purely in terms of physics. So yeah, we'll call it here, and then we'll see you next week. So if you have any question, let me know.